In this video, I'm going to show you how you can use the squeeze theorem to find certain limits for functions of two variables. Now, I'm also going to use this additional property of limits here that says that the limit of a function is equal to 0 if and only if the limit of the absolute value of that function is also equal to 0. So the squeeze theorem, which you may have seen in Calculus 1 with functions of one variable, basically says if you have one function that's sort of squeezed in between two other functions, there's one function that's below it and one function above it, then if the lower function and the upper function both have the same limit, then the function in the middle also has to have the same limit because it sort of gets squeezed in between the other two, so it's forced to have the same limit at that particular value if we're talking about one dimensions, or at the particular point if we're talking about functions with two variables. So let's find this limit here, the limit of xy over the square root of x squared plus y squared. Now, first thing I want to note is that notice if we let y equal 0, so if y was equal to 0, that would make this numerator equal to 0 and the denominator would just be square root of x squared. So if we allowed the point xy to approach 0, 0 along the line y equals 0, in other words along the x-axis, then the limit would appear to be 0 if we approached it from that direction, because you have 0 over x squared, or 0 over the square root of x squared, and 0 divided by anything is 0. Same thing if we let x equal 0, then this numerator would also equal 0, and the denominator would be the square root of y squared, which is just y. So if we let xy approach 0, 0 along the y-axis, then it would also approach 0. So we might guess that this limit is equal to 0. You could also check, like, approaching from different directions, like if you let y equal x, if you replace the y's with x's, you would get x squared over the square root of 2x squared, because this would also be an x squared here. And you would see that that would also approach 0 as well. Although, yeah, because then you would just have x squared over the square root of 2 times x, and then the x would cancel, so you just get x over square root of 2, which would approach 0 if x approaches 0. So we might suspect this limit is equal to 0, because if we approach this point from various different directions, we keep getting 0. However, that does not prove it, remember. To prove it, we'd have to show it for all infinitely many paths. So we're going to prove it using the squeeze theorem, that this limit is equal to 0. And what I'm going to start by doing is I'm going to start by looking at the absolute value of this. So the absolute value of this function so I'm going to take the absolute value of the whole thing. Well, first of all, I know that this is now greater than or equal to 0. That's just from the definition of absolute value. If I take the absolute value of anything, it's always going to be greater than or equal to 0. And I know that the limit of 0 is equal to 0. So this is like my f of x function that I'm looking for, or my f of xy function that I'm looking for is just a constant function 0, because I know the limit of that one is equal to 0. So I'm going to try to find a function that's greater than this, greater than or equal to this, that is also approaching 0. Okay, so if I take absolute value here, then I can split this up. I can write this as absolute value of x times absolute value of y over the absolute value of this, but I know this denominator is always positive anyways, because x squared is always positive since it's squared, and y squared is always positive, and then the square root of a positive number is always positive, so I don't need the absolute value around the denominator. Now this, I'm going to justify this in a second here, but I do know that this function is less than or equal to the absolute value of x times the square root of x squared plus y squared over the square root of x squared plus y squared. So what I did here was I replaced the absolute value of y in the numerator with the square root of x squared plus y squared, and I used less than or equal to. So to justify this is because the absolute value of y is always less than or equal to, well, actually let me do this in 2 steps. The absolute value of y is the same as the square root of y squared. That's sort of another definition of absolute value. if you take the square root of something squared, you can't really just cancel the square root with the square root unless you know that the number y is positive. If y could be positive or negative, then the square root of y squared is not just equal to y, it's equal to the absolute value of y. And I know that the square root of y squared is less than or equal to the square root of x squared plus y squared, because I know that x squared, since it's squared, is always a positive number. So that means if I take y squared and I add something positive to it, then it's going to be bigger than y squared with nothing else added to it. So the square root of y squared is less than or equal to the square root of x squared plus y squared, because y squared is less than or equal to the square root of x squared plus y squared. So that justifies this here. If I replace the absolute value of y with the square root of x squared plus y squared, then it's no longer equals, but I can say it's less than or equal to, because this is less than or equal to that. Now the reason I did this is because now I can cancel this and I get a simpler function. This gives me the function absolute value of x. So for my squeeze theorem, this is like my f of xy. This is my middle function, my g of xy. And this is my upper function, my h of xy. So I have one function that's between two others. Imagine this if we graph these functions in 3 dimensions. If we look up and down the z-axis, this would be the bottommost function. This would be the horizontal plane, the xy plane, where z is 0. This would be somewhere above the xy plane, and then this function here would be further above that. Okay, so we know that, so let's say since the limit as xy approaches 0, 0 of this function is equal to 0, obviously, because the limit of a constant is a constant, so the limit of 0 is 0, and that's also the limit of absolute value of x, because if we let x approach 0, then this just becomes absolute value of 0, which is 0. So since those two limits are 0, by the squeeze theorem, we must also have the limit as xy approaches 0, 0 of our g of x function. Actually, I'm being a little bit consistent here. If I'm inconsistent here. If I'm going to use absolute value of x here, then I should just put 0 here. Or I should call this one f of xy and this one h of xy. It doesn't matter. I'm just trying to be consistent. Then we know that the limit of this, the middle function, is equal to 0 as well. But if the absolute value of that function, its limit is 0, then this implies that the limit of the same function without the absolute value also has to be equal to 0. So we found the limit. Now, one thing I do want to mention here at the end is be careful, this property that I used here only works when both of these limits are equal to 0. So for example, if you find that the limit of the absolute value of a function equals 2, that does not mean that the limit of the original function has to equal 2. In fact, it doesn't even mean the limit of the original function has to exist at all. This only works specifically when the limit is 0 on both sides. Okay, so that's how we can use the squeeze theorem.